back in the early 20th century, astronomer Milankovitch actually came up with a set of theories that actually tried to explain some of the sort of asymmetries in Earth-Sun relationships. Okay, and in particular, that's important from a climate perspective because we can see that these sort of asymmetries in our orbit can result in pretty strong seasonal contrasts between the northern hemisphere and the southern hemisphere. Okay, and so there are these three basic properties, and I inferred them earlier. We'll go through them one by one here. But the three sort of, reasons why the world's not perfect, if you want to blame them, you might blame these three reasons. One is the shape of the Earth's orbit, whether it's a circular orbit or whether it's more oval, and that's a term called eccentricity. Okay, and it turns out that the Earth's orbit actually changes. It goes from becoming more circular to becoming more eccentric about every 100,000 years. Okay, and all these properties here involving Milankovitch theory are all sort of based in astronomy and based on the gravitational pull of planets and the sun. Okay, along with some of the basic ideas of how the Earth is actually a rotating body in space, and just like most rotating bodies, when you take a top and you spin it, you realize that top is spinning, but it also wobbles through time. And that brings us to the second term here, which is precession. And this is basically how the Earth actually wobbles about its axis. So the Earth is spinning, right? And again, you spin a top, eventually it'll wobble. It'll actually go through a 180 or a 360. So that precession term actually means that the Earth actually changes its orientation. Right now, currently, the North Star is north, right? So the North Star is north. And the Earth is actually rotating, right? And it's rotating. And eventually it's going to wobble such that 11,000 years from now, the North Star will be not north. It'll be northeast, northwest. It'll be rotating. It's not going to be north. It's not going to be true north. Okay, we're going to be in a different sort of plane in our orbit due to the sort of wobble of the Earth about its axis. Okay, and then the last term here is changes in the tilt of the Earth's axis. So the Earth has this tilt of 23.5 degrees, right? And it turns out that it changes just a tad through time. It becomes more exaggerated, less exaggerated through time. And it goes through that process called obliquity every 41,000 years. Okay, so first of all, we've talked a lot about 100,000 years and 41,000 years, and we're talking about this, so these things must be related to sort of orbital changes in climate, and that would be correct. And let's go through this in a little bit more detail, but I'll start it off by showing you again, this is a picture of the cryospheric coverage in our current climate. Okay, we looked at this last time, and what we realized pretty quickly, and if I show you, especially if I showed you sort of the seasonal cycle here, is that we have a lot more sort of landmass at high latitudes in the northern hemisphere. Okay, and clearly, Greenland sticks out there like a sore thumb. So what this means is that our current configuration of our continents is such that we have the ability to actually form ice over our continents. And again, it's easier to form ice over continents versus over open ocean. It's easier to form ice in the northern hemisphere over land than it is in the southern hemisphere, just because we don't have that much land mass at sort of the right latitudes in the southern hemisphere. We have Greenland, but it's way far south. We don't have much land mass here between, say, 60 degrees and 75 degrees south. Okay, but we do have quite a bit of that in the northern hemisphere, and that's really good for building ice sheets or getting rid of ice sheets. Okay, so keep that in mind, and we've had this sort of configuration of our continents for the last 6 million years, give or take. Okay, this has not changed over that time period. Okay, so we'll go through these three terms here of eccentricity, obliquity, and precession. And again, here's eccentricity. This is a 100,000 year cycle. Okay, and again, we all know of someone who's eccentric. They're a little off. They're not circular. They're an oval. Okay, so eccentricity refers to that shape of that orbit. A more eccentric orbit means that we have an orbit that looks more like this. Okay, it doesn't get this exaggerated, by the way, but special effects are limited in this course, so we're going to use them when we can. Okay, this is a very, very eccentric orbit. And again, if you'll recall here, we have an orbit that's not also symmetric, such that the sun is going to be a different distance from the Earth depending on where the Earth is in its orbit. Okay. Oops. So, you can take a look at sort of this sort of eccentricity idea, and if you go between a sort of very circular orbit, right? And this is almost symmetric, if you will. And you look at sort of the Earth in this picture here, and the orientation. And this is, in this case, this would be southern hemisphere summer, right? Southern hemisphere is pointed at the sun, right? And if we were to take it 180 few days, further in time, we'd have the Earth over here, and we would have northern hemisphere summer as well. We'd have pretty much equal amounts of energy in northern hemisphere summer and southern hemisphere summer. It wouldn't be very different. Okay, we can contrast that with this orbit. With this orbit, here is southern hemisphere summer. It's quite close to the sun. Okay, whereas if we were to take again the Earth and basically allow it to go on its track for 180 some odd days, we would eventually be over here during northern hemisphere summer, and in northern hemisphere summer we'd be super far away from the sun. Okay, solar constant would be much, much lower. And if the solar constant was much, much lower in the summer, what do you think that's going to do to glaciers? Help them stay around. Yeah, help them stay around, absolutely. It's not going to be warm in summer in the northern hemisphere, where we actually have landmass, where glaciers can form. Okay, that's going to be the theme we'll talk about through all these orbital cycles. Here's our sort of estimate of eccentricity. And again, these can be estimated through our understanding of sort of astronomy and planets. Okay, and reality is eccentricity is quite small. We don't have crazy orbits with, an eccentricity of 1 is way out there, crazy. But we can see a fairly obvious 100,000 year cycle. There's sort of a longer time period built in here as well. But the sort of peak to peak here is on the order of 100,000 years. Okay? Going from being more circular to being more eccentric. Okay? Let's move on to talk about obliquity. And obliquity, again, is this sort of change in the tilt of the Earth. So this is how we see globes today. When a globe is on a desk, it's always tilted a little. I don't know if it's ever worthwhile taking a protractor and checking it out, whether it's 23.5 or whether it's actually an Earth that's super old. It's actually an antique globe from about 20,000 years ago, and it tilts just off of it. Just saying. Okay. So what we actually know is that through time, the tilt of the Earth changes just a smidge. It goes between 22.1 degrees, right? It's kind of the most normal it's going to be, and then it goes to a more exaggerated 24.5 degrees. Small changes in the tilt of the Earth. Doesn't seem super important, right? During June 21st, right, the tilt of the Earth is 23.5 degrees today. What if the tilt of the Earth was 90 degrees? What that would mean, if the tilt of the Earth was 90 degrees, that would mean that during June 21st, the North Pole would be directly facing the sun. It'd be like the North Pole became the equator, or the solar equator. Okay, and if you were in a situation like that, it'd be very hard to actually have ice. You wouldn't have ice. It would be gone. Okay? Whereas the opposite, if we had no tilt of our Earth, okay, it was not tilted, what would happen on our planet? If we had no tilt. We wouldn't have seasons. Yeah, that'd be really, really different. It would be really good. You'd have a really good chance of actually forming ice sheets. Okay, really good chance. Once you start to form those ice sheets, eventually they're going to have this nice feedback process, and eventually you have something really interesting happening in terms of climate. Okay, so this changes through time, 41,000 years, and again that corresponds with the sort of 41,000 year cycle that we saw from about 3 million years ago to about 1 million year ago. 1 million year ago. Okay, and then the last term here is precession, and this is this term that's basically wobble of the Earth. And so I like this figure here. right? This is our sort of tilt of the Earth today, and it's 23.5 degrees. It's not going to change, changes in the future, so be it. But the Earth is actually also wobbling through time. So currently, here's our Earth today. Here's the tilt. We're pointing towards Polaris, which is our current North Star. But here 14,000 years, or 11,000 years ago, or 14,000 years ago, okay, the wobble is such that actually Vega would have been our pole star, would have been the North Star. Okay? So all these things are changing through time, and it turns out that the wobble is actually going to be pretty important.